Hello guys, welcome back to my channel. Today we are going to talk about reinforcement learning from human feedback and PPO. So reinforcement learning from human feedback is a technique that is used to align the behavior of a language model to what we want the language model to output. For example, we don't want the language model to use curse words, or we don't want the language model to behave in an impolite way to the user. So we need to do some kind of alignment. And reinforcement learning from human feedback is one of the most famous techniques, even if there are now new techniques like DPO, which I will talk about in another video. Now, reinforcement learning from human feedback is also how they created ChatGPT, so how they aligned ChatGPT to the behavior they wanted. In the topics of today are, first I will introduce a little bit the language models, how they are used and how they work. Then we will talk about the topic of AI alignment, why it's important. And later we will do a deep dive into reinforcement learning from human feedback. In particular, I will introduce first of all what is reinforcement learning. Then I will describe all the setup of the reinforcement learning. So the reward model, what are trajectories. In particular, we will see the policy gradient optimization and we will derive the algorithm. We will see also the problems with it, so how to reduce the variance, the advanced estimation, importance sampling of policy learning, etc. etc. The goal for today's video is actually to derive the loss of the PPO. So I don't want to just throw the formula at you, I want to actually derive step by step all the algorithm of PPO and also show you all the history that led to it. So what were the problems that PPO was trying to solve from a mathematical point of view. And in the final part of the video, we will go through the code of an actual implementation of reinforcement learning from human feedback with PPO. And I will actually not code from by line, I will actually explain the code line by line, and in particular I will show the implementation as done by the Hugging Face team. So I will not show you how to use the Hugging Face library to use reinforcement learning from human feedback, but we will go inside the code of the Hugging Face library and see how it was implemented by the Hugging Face team. This way we can combine the theory that we have learned with the practice. Now, the code written by the Hugging Face team is kind of obscure and complex to understand, so I deleted some parts and I also commented with my own comments some other parts that were not easy to understand. This way I hope to make it easier for everyone to follow the code. Now, there are some prerequisites before watching this video. First of all, I hope that you have some notions of probability and statistics, not much, at least you know what is an expectation. We need to know, so of course, some knowledge from deep learning, for example, gradient descent, what is the loss function, and the fact that in gradient descent we calculate some kind of gradient, etc. We need to have some basic knowledge of reinforcement learning, even if I will review most of it, so at least you know what is an agent, the state, the environment, and the reward. One important aspect of this video is that we will be using the transformer model a lot, so I recommend you watch my previous video on the transformer if you have not, if you're not familiar with the concept of self-attention or the causal mask, which will be key to understanding this video. So the goal of this video is actually to combine theory with practice. So I will make sure that I will always kind of give an intuition to formulas that are complex. And don't worry if you don't understand everything at the beginning. Why? Because I will be giving a lot of theory at the beginning, because later I will be showing the code. I cannot show the code without giving the theoretical knowledge. So don't be scared if you don't understand everything, because when we will look at the code, I will go back to the theory line by line so that we can combine, you know, the practical and the theoretical aspect of this knowledge. So let's start our journey. Okay. What is a language model? First of all, a language model is a probabilistic model that assigns probabilities to sequence of words. In particular, a language model allows us to compute the probability of the next token given the input sequence. In particular, for example, if we have a prompt that says Shanghai is a city in, what is the probability that the next word is China, or what is the probability that the next word is Beijing or cat or pizza? This is the kind of probability that the language model is modeling. Now, in my tractation of language model, I always make a simplification, which is that each word is a token and each token is a word. This is not always the case because it depends on the tokenizer that we are using. And actually, in most cases, it's not like this. But for simplicity, we will always consider for the rest of the video that each word is a token and each token is a word. Now, You may be wondering, how can we use the language models to generate text? Well, we do it iteratively, which means that if we have a prompt, for example, a question like where is Shanghai, then we ask the language model what is the next token, and for example, greedily we select the token with the most probability. So we select, for example, the word Shanghai. Then we take this word Shanghai, let me use the laser, we put it back into the input, and we ask again the language model what is the next token, and the language model will tell us what are the probability of the next token, and we selected the one that is more probable. Suppose it's the word is. We take it and we put it back in the input, and again we ask the language model what is the next token. Suppose the next token is in. We take it, we put it back in the input, and we ask again the language model what is the next token, etc., etc., until we reach a number of tokens that we have generated, or we believe that the answer is complete. So in this case we can stop, for example, because we can see that the answer is Shanghai is in China, is the answer generated by the language model. So this is an iterative process of generating text with the language model, and all language models actually work like this. Now, with what is the topic of AI alignment? A language model is usually pre-trained on a vast amount of data, which means that it has been pre-trained on billions of web pages or the entire of Wikipedia or thousands of books. This gives the language model a lot of knowledge from which it can retrieve and it can learn to complete a prompt in a reasonable way. However, this does not teach the language model to behave in a particular way. For example, just by pre-training, we do not teach the language model to not use offensive language, or to not use racist expressions, or to not use curse words. To do this, and to create, for example, a chat assistant that is friendly to the user, we need to do some kind of alignment. So the topic of AI alignment is to align the model's behavior with some desired behavior. Let's talk about reinforcement learning. So reinforcement learning is an area of artificial intelligence that is concerned with training an intelligent agent to take actions in an environment in order to maximize some reward that it receives from the environment. Let me give you a concrete example. So imagine we have a cat that lives in a very simple world. Suppose it's a room made up of many grids, and this cat can move from one cell to another. Now, in this case, our agent is the cat, and this agent has a state, and which describes, for example, the position of this agent. In this case, the state of the cat can be described by two variables. One is the x coordinate, and one is the y coordinate of this of the position of this cat. Based on the state, the cat can choose to do some actions, which could be, for example, to move down, move left, move right, or move up. Based on the state, the cat can take some actions, and every time the cat takes some action, it will receive some reward from the environment. It will for sure move to a new position, and at the same time will receive some reward from the environment. And the reward is according to this reward model. So if the cat moves to an empty cell, it will receive a reward of 0. If it moves to the broom, for example, it will receive a reward of -1 because my cat is scared of the broom. If somehow, after a series of states and actions, the cat arrives to the bathtub, it will receive a reward of -10 because my cat is super scared of water. However, if the cat somehow manages to arrive to the meat, it will receive a big reward of +100. How should the cat move? Well, there is a policy that tells what is the probability of the next action given the current state. So the policy describes for each position, so for each state of the cat, with what probability the cat should move up or down or left and right. And then the agent can choose to either choose randomly an action, or it can choose to select the action with the most probability, for example, which is a greedy strategy, etc., etc. Now, the goal of reinforcement learning is to learn a probability, so to optimize a policy such that we maximize the expected return when the agent acts according to this policy, which means that we should have a policy that with very high probability takes us to the meat, because that's one way to maximize the expected return in this case. Now, you may be wondering, okay, the cat, I can see it as a reinforcement learning agent, and the reinforcement learning setup makes sense for the cat and the meat and all these rewards. But what is the connection between reinforcement learning and the language models? Let's try to clarify this. So, You can think of the language model as a policy itself. So, as we saw before, the policy is something that, given the state, tells you what is the probability of the action that you should take in that state. In the case of the language model, we know that the language model tells you, given a prompt, what is the probability of the next token. So we can think of the prompt as the state and the next token as the action that the language model can choose to perform, which will lead to a new state, because every time we sample a next token, we put it back into the prompt, then we can ask the language model again what is the next token, etc. So as you can see, we can think of the language model as the reinforcement learning agent itself, and also as the policy itself, in which the state is the prompt and the action is the next token that the language model will choose according to some strategy, which could be the greedy one, which could be the top P or the top K, or etc, etc. The only thing that we are missing here is the reward model. How can we reward the language model for good responses, and how can we kind of penalize the language model for bad responses? This is done through a reward model that we have to build. Let's see how. Okay, imagine we want to create a reward model for our language model, which will become our reinforcement learning agent. Now, to reward the model for generating a particular answer for questions, we could create a data set like this of questions and answers generated by the model. For example, imagine we ask the model, where is Shanghai? The language model could say, okay, Shanghai is a city in China. We should give some reward to this answer, so how good this answer is. Now, in my case, I would give it a high reward because I believe that the answer is short and to the point. But some other people may think that this answer is too short, so they maybe they prefer an answer that is a little longer. Or in this case, for example, what is 2 plus 2? Suppose that our language model only says the word 4. Now, in my case, I believe this answer is too short, so it could be a little more elaborate, but some other people may think that this answer is good enough. Now, what kind of reward should we give to this answer or this answer? As you can see, it's not easy to come up with a number that can be accepted by everyone. So, us humans are not very good at finding a common ground for agreement, but unfortunately, we are very good at comparing. So, we will exploit this fact to create our data set for training our reward model. So what if instead of generating one answer, we could generate multiple answers using the same language model? This can be done, for example, by using a high temperature. And then we can ask a group of people, so expert labelers, experts in this field, to choose which answer they prefer. And having this data set of preferences, we can then create a model that will generate a numeric reward for each question and answer. So first we create a data set of questions, then we ask the language model to generate multiple answers for the same question, for example, by using a high temperature, and then we ask people to choose which answer they prefer. Now our goal is to create a neural network which will act as a reward model, so a model that, given a question and an answer, will generate a numeric value for in such a way that the answer that has been chosen should have a high reward, and the answer that has not been chosen, which is something that we don't like, should have a low reward. Let's see how it is done. What we do in practice is that we take a pre-trained language model. For example, we can take the pre-trained llama, and we feed the language model the question and answer. So the input tokens here, you can see, are the questions and the answer concatenated together. We give it to the language model as input. The language model, it's a transformer model, so it will generate some output embeddings. These are called hidden states. So as you know, the input are the tokens, which are converted into embeddings, then the positional encoding, then we feed it to the transformer layer. The transformer layer will actually output some embeddings, which are called hidden states. And usually for text generation, we take the last hidden state, we send it to some linear layer, which will project it into the vocabulary, then we use the softmax, and then we select the next token. But instead of selecting, because here we do not want to generate a text, we just want to generate a numeric reward, we can substitute the linear layer that is projecting the last hidden state into the vocabulary, but instead we replace it with another linear layer with only one output feature. so that it will take an input embedding as input and generate only one value as output, which will be the reward assigned to the response, to the answer for the particular given question. Of course, this kind of model, this is the architecture of the model. We also need to train it. So we also need to tell this model that it has to generate a high reward for answers that are chosen and low reward for answers that are not chosen. Let's see what is the loss function that we will use to train this model. The loss function that we will be using is this one here. So you can see it's minus the log of the sigmoid of the reward assigned to the good answer minus the reward assigned to the bad answer. Now, let's analyze this loss function here. So, pen, okay. So there are two possibilities. Either this difference here, so he is negative, or it is positive, which means that either the response assigned to the, so how do we train it? First of all, basically, because our dataset is made up of questions and possible answers, I suppose there are only two possible answers, one is the good one and one is the bad one. We take each question answers, we feed the question to the model along with the answer concatenated to it, and the model will generate some reward. We do it for the good question and for the for the good answer and also for the bad answer, and it will generate two rewards. Suppose this is the reward for the good one, so let's write good one, and this is the reward associated with the bad one. Now, either the model assigned a high reward to the good one and a low reward to the bad one, so this difference will be positive and this is good. So in this case the loss will be like this. So if the reward given to the good answer is higher than the reward given to the bad answer, this difference will be positive. So let's see the sigmoid function, how does it behave when the input is positive. So when the input is positive, the sigmoid gives an output value that is between 0.5 and 1. So this stuff here will be between 0.5 and 1. When the log receives an input, because here you can think of as having a parenthesis, when the log sees an input that is between 0.5 and 1, will generate a number, negative number, that is more or less between 0 and -1, more or less. So with the minus sign here, it will become a positive number between 0 and 1. So the loss in this case will be small because it will be a number between more or less between 0 and 1. Maybe it's 2 or 3, but okay, depends on the graph of the log. I don't remember what is the exact value for the 0.5 here. However, let's see if the model gave a high score to the bad response and a low score to the good response. So let's start again. Okay. And okay, here is the bad response and here is the good response. Now, what happens if this value here is smaller than this value here? So this difference will be negative. When the sigmoid receives as input something that is negative, it will return an output that is between 0 and 0.5. The log, when it sees an input that is between 0 and 0.5, so more or less here, it will return a number, negative number, that is between -infinity and more or less 1. So it will return, because there is a minus sign here, it will become a very big number in the negative range. So the loss in this case will be big, so big loss. Here it was a small loss. Small loss. Okay. Now, as you can see, when the reward model is giving a high reward to the good answer and a low score to the bad answer, the loss is small. However, when the reward model gives a high reward to the bad answer and a low score to the good answer, the loss is very big. What does it mean this for the model? That it will force the model to always give high rewards to the winning response and low reward to the losing response. So because that's the only way for the model to minimize the loss, because the goal of the model always during training is to minimize the loss. So the model will be forced to give high reward to the chosen answer and low reward to the not chosen answer or the bad answer. In Hugging Face, this reward model is implemented in the reward trainer class. So if you want to train your own reward model, you need to use this reward trainer class, and it will take as input a auto model for sequence classification, which is exactly this architecture here. So it's a transformer model with, instead of having the linear layer that projects into the vocabulary, it has a linear layer with only one output feature that gives the reward. And if you look at the code on how this is implemented in the Hugging Face library, you will see that they first generate the reward for the chosen answer, so for the good answer. Then they generate the reward for the bad answer, so for the rejected response, here it's called. And then they calculated the loss exactly using the formula that we saw. So the log sigmoid of the rewards given to the chosen one minus the rewards given to the rejected one. Let's talk about trajectories now. Now, as I said previously, in reinforcement learning, the goal is to select a policy or to optimize a policy that maximizes the expected return of the agent when the agent acts according to this policy. More formally, we can write it as follows: that we want to select a policy pi that gives us the maximum expected reward when the agent acts according to this policy pi. Now, what is the expected return? The expected return of the policy is the expected return over all possible trajectories that the agent can have when using this policy. So it's the expected return over all possible trajectories. As you know, the expectation can also be written as an integral, so it is the probability of the particular trajectory using this policy multiplied by the return over that particular trajectory. Now, what is a trajectory, first of all, and later we will see what is the probability of a trajectory. So the trajectory is a series of states and actions, which means that a trajectory you can think of in the case of the cat as a path that the cat can take. Suppose that each of the trajectory have a maximum length, so we don't want the agent to perform more than 10 steps to arrive to its goal. Now the cat can go to the meat, for example, using this path here, or it can choose this path here, or it can use this path here, or this one here, or for example, it can go forward and then go backward and then stop because it has already used the 10 steps, or it can go like this, etc., etc. So there are many paths. What we want is we want to find a policy that maximizes the expected return, so the return that we get along each of these paths. Now we will also model the next state of the cat as being stochastic. So first of all, let's introduce what is these states and actions. So let me give you an example. Suppose that our cat is starting from some state S0, which is the initial state. The policy tells us what is the next action that we should take given the state. So the cat will ask the policy what is the next action that it should take. And because the policy is stochastic, the policy will tell us what is the probability of the next action. So just like in the case of the language model, we given a prompt, we select what is the probability of the next token. So imagine that the policy tells us that the cat should move down, so action down, for example, with very high probability, or it should move right with lower probability, it should move left with even lower probability, or it should move up with an even lower probability. Suppose that we select to move down, it will result in a new state that may not be exactly this one. Why? Because we modeled the cat as being drunk, which means that the cat wants to move down but may not always move down, and we will see later why this is helpful. But another case could be, for example, imagine we have a robot and the robot wants to move down, but the wheels of the robot are broken, so the robot will not actually move down, it will remain in the same state. So we always model the next state not as being deterministically determined, but as being stochastic given the current state and the action that we choose to perform. So imagine that we choose to perform the action down. The cat may arrive to a new state, S1, which will be according to some probability distribution. Then we can ask again the policy, what is the next action I should do? The policy may say, okay, you should move right with very high probability, and you should move down with a lower probability, or you should move left with an even lower probability, etc., etc. So as you can see, we are creating a trajectory, which is a series of states and actions which define how our cat will move in a particular trajectory. Okay, let's see. Now, what is the probability of a trajectory? The probability of a trajectory, as you can see here, the fact that we chose a particular action depends only on the state we were in. And the fact that we arrived to this state here depended on the state we were in and the action that we have chosen. And then the fact that we have chosen this action here depended only on this state we were in, because the policy only takes as input the state and gives us what is the probability of the action that we should take. So we can, because they are independent from each other, these events, we can multiply them together to get the probability of the trajectory. So the probability of the trajectory is the probability of starting from a particular starting point, so from this state 0 here. Then for each step that we have taken, so for each action state of this particular trajectory, we have the probability of choosing the action given the state, and then to arriving a new state given that we were at this state at time step t, and we chose action at time step t. And we multiply all these probabilities together because they are independent from each other. Another thing that we will consider is that how do we calculate the reward of a trajectory? A very simple way to calculate the reward of a trajectory is to just sum all the rewards that we get along this trajectory. For example, imagine the cat to arrive to the meat follows this trajectory. You could say that the reward is 0 here, so it's 0, 0, 0, 0, 0, 0, 0, and then suddenly it becomes plus 100 when we reach the meat. If the cat, for example, follows this path here, we could say, okay, it will receive -1 because the cat is scared of the broom, then 0, 0, 0, 0, 0, 0, 100. Actually, this is not how we will calculate the reward of a trajectory. We will actually calculate the reward as discounted, which means that we prefer immediate rewards instead of future rewards. To give you an intuition in why this happens, first let me talk about money. So if I give you $10,000 today, you prefer receiving it today instead of receiving it in 1 year. Why? Because you could put the $10,000 in the bank, it will generate some interest, so at the end of the year you will have more than $10,000. And in the case of reinforcement learning, this is helpful also for another case. For example, imagine the cat can only take 10 steps to arrive to the meat, or 20 steps. So one way for the cat to arrive to the meat is to just go directly to the meat like this, and this is one trajectory. But another way for the cat is to go like this. For example, go here, then go here, then go here, then go here, and then go here. So in this case, we prefer the cat to go directly to the meat instead of taking this longer route. Why? Because we modeled the next state as being stochastic, and if we take a longer route, the probability of ending up in one of these obstacles is higher the longer the route is. So we prefer having shorter routes in this case. And this is also convenient from a mathematical point of view to have these discounted rewards, because this series, which is infinite in some cases, okay, we will not work with infinite series, but it's helpful because this series can converge if this element of the series is becoming smaller and smaller and smaller. So let me give you a practical example of how to calculate the reward in a discounted case. So imagine the cat starts from here, and it goes to the follows this path. So to calculate the reward of this trajectory, we will do like this. So it is the reward at time step 0, which is arriving to the broom, multiplied by gamma to the power of 1. So it will be gamma multiplied by -1. Then all these rewards are 0, 0, 0, so they will not be summed up. And finally, we arrive here at where the reward is plus 100 at time step 1, 2, 3, 4, 5, 6, 7, 8. So it will be gamma to the power of 8 multiplied by 100. So gamma is usually not usually, it's always something that is between 0 and 1. So it's a number smaller than 1. So it means that we are decaying this reward by gamma to the power of 8. So it will be smaller the longer we take to reach it. This is the intuition behind discounted rewards. Now you may be wondering, the trajectories make sense in the case of the cat, so I can see that the cat will follow some path to arrive to the meat, and it can take many paths to arrive to the meat, so we know what is the trajectory in the case of the cat. But what are the trajectories in case of language model? Well, as I saw before, we have a policy, which is the language model itself. So because the policy tells us, given the state, what is the next action, and in the case of the language model, we can see that the language model itself is a policy, and we want to optimize this policy such that it selects the next token in such a way as to maximize a cumulative reward according to the reward model that we have built before using the dataset of preferences that I saw before. Also, in the case of the language model, the trajectory is a series of states and actions. What are the states in the case of the language model? Are the prompts. What are the actions? Are the next tokens. So imagine we have a question like this for the language model. So where is Shanghai? Of course, we will ask the language model what is the next token, which this will become the initial prompt, so the initial state of the language model. We will ask the language model what is the next token, and that will become our action, the token that we choose. But then we feed it back to the language model, so it will become the new state of the language model. And then we ask the language model again, what is the next token? It will be, for example, the word is, and this will become again the input of the language model, so the next state. And then we ask the language model again, what is the next token? For example, we choose the token in, and then the concatenation of all these tokens will become the new state of the language model. So we ask the language model again, what is the next token, etc., until we generate an answer. So as you can see, also in the case of the language model, we have trajectories, which are the series of prompts and the tokens that we have chosen. Now imagine that we have a policy, because our goal is to optimize our language model, which is a policy, such that we maximize a cumulative reward according to some reward model that we have built in the past. Now more formally, our goal is this. So we want to maximize this function here, which is the expected return over all possible trajectories that our language model can generate. And we also saw that before, the trajectory is a series of prompts and next tokens. Now, when we use a stochastic gradient descent, so for example, when we try to optimize a neural network, we use stochastic gradient descent, which means that we have some kind of loss function. We calculated the gradient of the loss function with respect to the parameters of the model, and we change the parameters of the model such that we move against the direction of this gradient. So we take little steps against the direction of the gradient to optimize the parameters of the model to minimize this loss function. In our case, we do not want to minimize a loss function, we want to maximize a function, which is here. And this can also be thought of as an objective function that we want to maximize. So instead of using a gradient descent, we will use a gradient ascent. The only difference between the two is that instead of having a minus sign here, we have a plus sign. Now, this algorithm is called the policy gradient optimization. And the point is we need to calculate the gradient of this function here, of our objective function. So what is the gradient with respect to the parameters of our model, so our language model? What is the gradient of the expected return over all possible trajectories with respect to the parameters of the model? We need to find an expression of this gradient so that we can calculate it and use it to optimize the parameters of the model using gradient ascent, using also a learning rate alpha you can see here. Now let's see how to derive the expression of the gradient of this objective function that we have. Now, the gradient of the objective function is the gradient of this expectation. So it's the expectation over all possible trajectory multiplied by the return over the particular trajectory. As we know, the expectation is also an integral, so it can be written as the gradient of the integral of the probability of following a particular trajectory multiplied by the return over this trajectory. As you know, from high school, the gradient of a sum is equal to the sum of the gradients, or you may recall it as the derivative. So the derivative of a sum of a function is equal to the sum of the derivatives. So we can bring this gradient sign inside, and it can be written like this. Now we will use a trick called the log derivative trick to expand this expression, so p of tau given theta, into this expression here. Let me show you how it works. Let's use the pen. Okay. You may recall also from calculus that the gradient with respect to theta of the log function of a function, in this case of p of tau given theta, is equal to, so the gradient of the derivative of the log function is 1 over the function p of tau given theta multiplied by the gradient with respect to theta of the function that is inside the log, so p of tau given theta. We can take this term to the left side, multiply it here, and this expression here will become equal to this expression multiplied by this expression, and this is exactly what you see here. So we can replace this expression that we see in the equation above, so this expression, with this expression we can see here in the equation below. Now, this integral, we can write it back as an expectation over all possible trajectories of this quantity here now, because the probability is only this term here. So we can write it back as an expectation. Now we need to expand this term here. So what is the gradient of the log? So this expression here. So what is the gradient of the log of probability of a particular trajectory given the parameters of the model? Let's expand it. We saw before that the probability of a trajectory is just the product of all the probabilities of the state actions that are in this trajectory. So the probability of starting from a particular state multiplied by the probability of taking a particular action given the state we are in, multiplied by the probability of ending up in a new state given that we started from the state at time step t and we took action at time step t. And we do it for all the state actions that we have in this trajectory. If we apply a log to this expression here, the product here will become a sum. And let's do it actually. Okay, so we call the log of p of tau given pi theta actually, because we model our policy pi as parameterized by parameter theta. Here I forgot the theta, but doesn't matter. It's equal to the log of all this expression, so it's the log of a series of products, so it can be written as the log of p0 of s0 plus the summation the log of p of st plus 1 given that we are in st plus at, not plus, and at, and we are in we took action at, plus the log of the action that we took according to our policy at, given that we were in st. Okay, now we are also taking the gradient of this expression, and as you can see here, there is no term that depends on theta, so it can be deleted. Also, in this case, we do not have any expression that, in this expression here, we do not have anything that depends on theta, so this can be deleted. Because the derivative of something that does not have the variable being derived is a constant, so it can be deleted because it will be 0. So the only term surviving in this summation is only these terms here, because it's the only one that contains the theta, as you can see here. So in the final expression is this one here, so this summation. Now let me delete. So we have derived an expression that allow us to calculate the gradient of the objective function. Because why we need the gradient of the objective function? Because we want to run gradient ascent. Now, one thing that we can see here, we still have this expectation over all possible trajectories. Now, to calculate over all possible trajectories, in the case of the cat, it means that we need to calculate this gradient over all the possible paths that the cat can take of length, for example, 10 steps. So if we want to model trajectories of only length 10, it means that we need to calculate all the possible paths that the cat can take of length 10. And it could be a huge number. In the case of language model, it's even bigger, because usually, imagine we want to generate trajectories of size 100. It means that what are the possible all the possible text that we can generate of size 100 tokens using our language model, and for each of them we need to calculate the reward and the log action probabilities, which I will show later how to calculate. Now, as you can see, the problem is this expectation is over a lot of terms, so it's intractable computationally to calculate this expression, because we would need to generate a lot of text for the language model. So one way to calculate this expectation is to approximate it with the sample mean. So we can always approximate an expectation with the sample mean. So instead of calculating it over all the possible trajectories, we can calculate it over some trajectories. So in the case of the cat, it means that we take the cat and we ask it to move using the policy for some number of steps, and and we will generate one trajectory. We do it many times, and it will generate some trajectories. In the case of the language model, we have some prompt. We ask the language model to generate some text. Then we do it many times using different temperatures and different sampling strategies. For example, by sampling randomly, instead of using the greedy strategy, we can use the top P, so it will generate many texts. Each text will represent a trajectory. We do not have to do it over all the possible text that the language model can generate, but only some. So it means that we will generate some trajectories. So we can calculate this expression here only on some trajectory that our language model will generate, and this will give us an approximation of this gradient here. Once we have this gradient here, we can evaluate it over the trajectories that we have sampled, and then run gradient ascent on it. So practically it works like this. In the case of the cat, we have some kind of neural network that defines the policy, which is taking the state of the cat, which is the position of the cat, tells us what is the probability of the next action that the cat should take. We can use this policy, which is not optimized, to generate some trajectories. So for example, we start from here, we ask the policy, where should I go? And for example, we use the greedy strategy and we move down. Then, or we use the top P, for example. Also in this case, we can use top P to sample randomly the action given the probabilities generated by the network. So imagine the cat goes down, and then we ask again the policy, where should I go? The policy may say, okay, move right, move down, move right, move down, etc., etc. So we will generate one trajectory. We do it many times by sampling always randomly according to the probabilities generated by the policy for each state actions. We will generate many trajectories in this case. Then we can evaluate, because we also know the rewards that we accumulate over each state actions, we calculate the reward. We also know the log probabilities of each action, because for each state we have the log, what was the probability of taking that action, and we choose it. And we need to calculate also the gradient of these log probabilities. This is done automatically by PyTorch when you run loss.dot backwards. So PyTorch actually will calculate the gradient for you. We do it for all the other possible trajectories. This will give us the approximated gradient over the trajectories that we have collected. We run a gradient ascent, and we optimize the parameters of the model using a step towards the gradient. Now, then we need to go, we need to do it again. So we need to collect more trajectories. We evaluate them, we evaluate the gradient of the log probabilities. We run a gradient ascent. So we take one little step towards the direction of the gradient. And then we do it again. We go again, collect some trajectories. We evaluate this expression here to calculate the gradient of the policy with respect to the parameters. and we run again gradient ascent, so a little step towards the direction of the gradient. This is known as the reinforcement learning algorithm in literature, and we can use it also to optimize our language model. So in the case of the language model, we have to also generate some trajectories. So one way to generate trajectories would be to, for example, use the database of questions and answers that we have built before for the reward model. Which means that we have some questions, so we ask the language model to generate some answer for each question using, for example, the top P strategy. So it will generate, according to the temperature, many different answers for the same given question. This will be a series of trajectories because the language model generation process is an iterative process made up of states, so prompts and actions, and which are the next tokens. And this will result in a list of trajectories for which we have the log probabilities, because the language model generates a list of probabilities over the next token. And we can also calculate the gradient of this state log probabilities using PyTorch, because when we run loss.backward, it will calculate the gradient. But how do we do it in practice? Let's see. Now we want to calculate this term here, so the log probabilities of the action given the state for language models, which means what is the probability of the next token given a particular prompt. Imagine that our language model has generated the following response. So we asked the language model, where is Shanghai? And the language model said Shanghai is in China. Our language model is a transformer model, so it is a transformer layer, and it will generate, given an input sequence of embeddings, it will generate an output sequence of embeddings, which are called hidden states, one for each input token. As you know, the language model, when we use it for text generation, it has a linear layer that allow us to calculate the logits for each position. So usually we calculate the logits only of the last token because we want to understand what is the next token. But actually we can calculate the logits for each position. So for example, we can also calculate the logits for this position, and the logits for this position will indicate what is the most likely next token given this input. So where is Shanghai? Question mark, Shanghai is. So this is because of the causal mask that we apply during the self-attention mechanism. So each hidden state actually encapsulates information about the current token, so in this case of the token is, and also all the previous tokens. This is a property of the language model, of the transformer model, that is used during training. So during training, as you know, we do not calculate the output of the language model step by step. We just give it the input sentence, the output sentence, which is the shifted version of the input sentence. We calculate the we do the forward pass, and then we calculate the log using only one forward pass. We can use the same mechanism to calculate the log probabilities for each states and actions in this trajectory, which, as I show you, is a series of prompts and next tokens. Now we can calculate the logits for this position, for this position, for this position, and for this position. Then usually we apply the softmax to understand what is the probability of the next token, but in this case we want the log probabilities, so we can apply the log softmax for each position. This will give us what is the log probability of the next token given only the previous tokens compared to the current one. So for this position it will give us the log probability of the next token given that the input is only where is Shanghai, question mark Shanghai. Of course, we do not want all the log probabilities, we only want the log probability of the token that actually has been chosen in this trajectory. What is the actual token that has been chosen for this particular position? Well, we know it, it's the word is. So we only select the log probability corresponding to the word is. This will return us the log probability for the entire trajectory, because now we have the log probability of selecting the word Shanghai given the state where is Shanghai. We have the log probability of selecting the word is given the input where is Shanghai, question mark Shanghai. We have the log probability of selecting the word in given the input where is Shanghai, question mark Shanghai is, etc, etc. So now we have the log probabilities of each position, of each state action in this trajectory. When we have this stuff here, we can always ask PyTorch to run the backward step to calculate the gradients, and then we multiply each gradient by the reward that we receive from our reward model. We can then calculate this expression, and then we can run gradient ascent to optimize our policy based on this approximated gradient. Let's see how to calculate the reward now for the trajectory. So calculating the reward is a similar process. As you saw before, we have a reward model that is a transformer model with a linear layer on top that has only one output feature. So imagine our sentence is the same. So where is Shanghai? Shanghai is in China. This is the trajectory that has been generated by our language model. Now we give it to the reward model. The reward model will generate some hidden states because it's a transformer model. And we apply the linear layer to all the positions that are corresponding to the action that are in this trajectory. So first action is the selection of this word, the second action is this one, the third and the fourth. So we can generate the reward for each time step. We can just sum these rewards to generate the total reward of the trajectory, or we can sum the discounted reward, which means that we will calculate something like this. For example, we will calculate, let's write it. So it will be the reward at time step 0 plus gamma multiplied by the reward at time step 1 plus gamma multiplied by the reward at time gamma to the power of 2 multiplied by the reward at time step 2 plus gamma to the power of 3 multiplied by the reward at time step 3, etc., etc. So now we also know how to calculate the reward for each trajectory. So now we know how to evaluate this expression you can see here. So now we know also how to run gradient ascent to optimize our language model. The algorithm that I have described before is called the gradient policy optimization, and it works fine for very small problems, but it exhibits problems. It is not perfect for bigger problems, so for example language modeling. And the problem is very simple. The problem is that we are approximating, so let's write here something. So we, as you saw before, our objective function, which is j of theta, which is an expectation over all possible trajectories that are sampled according to our policy, and expectation each one with its reward along the trajectory. So we are approximating the expectation with a sample mean. So we do not calculate this expression over all possible trajectories, we calculate it only on some trajectories. Now this is fair. It means that the result that we will get will be an approximation that on average will converge to the true expectation. So it means that on the long term it will converge to the true expectation, but it exhibits high variance. So to give you an intuition into what this means, let's talk about something more simple. For example, imagine I ask you to calculate the average age of the American population. Now, the American population is made up of 330 million people. To calculate the average age means that you need to go to every person, ask what is their birthday, calculate the age, and then sum all these ages that you collect, divide by the number of people, and this will give you the true average age of the American population. But of course, as you can see, this is not easy to compute because you would need to interview 330 million people. Another idea would be say, okay, I don't go to every American person, I only go to some Americans, and I calculate their average age, which could give me a good indication of what is the average age of the American population. But the result of this approximation depends on how many people you interview, because if you only interview one person, it may not be representative of the whole population. Even if you interview 10 people, it may not be representative of the whole population. So the more people you interview, the better. And this is actually a result that is statistically proven by the central limit theorem. So let's talk about the variance of this estimator. So we want to calculate the average age of the American population. Suppose that the average age of the American population is 40 years or 45 years or whatever. If we approximate it using a sample mean, which means that we do not ask every American but some Americans what is their average age, we need to sample randomly some people and ask what their age. Suppose that we only interview one person because we do not have time. Suppose that we are unlucky and this person happens to be a kindergarten student, and this person will probably say the age is 6. So we will get a result that is very far from the true mean of the population. On the other hand, we may ask again some random people, and these people happen to be, for example, all people from retirement homes. So we will get some number that is very high, which is, for example, 80 years, which is also not representative of the true population. So the smaller the sample, the more unlucky we are in getting these values that are very far from the true mean. So one way is to increase the sample size. So if we ask 1,000 people what is their average age, very probably we'll get something that is closer to this 40 years old, because we cannot be so unlucky to get 6 or that all of them happen to be in the kindergarten or in the retirement age, in the retirement home. This happens also when we approximate an estimation with a sample mean here. It depends, the quality of this approximation depends on how many trajectories we choose. And as you saw before, choosing too many trajectories from language models is not easy, because it means that you need to run inference on the language model many times to calculate these trajectories. Now, the problem is we cannot easily increase the number of trajectories, but we need to find a way to reduce this variance. So we do not, because this is the this tells us what is the direction of the gradient that we will use to run a gradient ascent. We want to find the true direction of the gradient. So imagine the true direction of the gradient is this one. If we have high variance, it means that sometimes this approximation may tell us that the gradient is actually pointing in this direction, or it's pointing in this direction, or it's pointing in this direction. But if we reduce the variance, it will probably tell us something that is more closer to the true direction of the gradient. So we will move our weights in a way that is moving to maximize the objective function, because we are moving according to the true direction of the gradient. So this is why we want to reduce the variance of this estimator. Now let's see what are the techniques that we can use to reduce the variance of this estimator without increasing the sample size. The first thing that we should notice is that, okay, first of all, we had this expectation that we approximate using the sample mean you can see here. Now, each of these log probabilities, so these log probabilities here, are multiplied by the reward over the entire trajectory. Now, the first thing that we should notice is that each action cannot alter the reward that we received in previous steps. So imagine we have a series of states and actions. So for example, we started from state 0, and then we take action 1, which led us action 0, and then this led us to state 1, in which we took action 1, which led us to state 2, in which we took action 2, etc, etc, etc. For each state action, we receive a reward, because when we take an action, it will, for example, in the cat, it will move to a new cell or remain in the same cell, and it will receive some reward. And also for this one, we will have some reward, so reward 1, and for this one, we will have reward 2. Now, when we take this action here, for example, action number 2, it cannot alter the reward that we already received in the past. So when we multiply by this term reward of tau, we do not consider all the rewards that came before the action that we are considering in this summation. So instead of calculating the reward for the trajectory starting from 0, we can calculate the reward starting from the time step of the action that we are considering for the log probabilities of the action. This term here is known as the rewards to go, which means what is the total reward if I start from this state and take this action and then act according to the policy for the rest of the trajectories. Why do we want to do this? Because as you can see, this expression here is an approximation of the true expectation here. The less terms we have, the better, because we will have less noise. Why? Because first of all, as we know, each action cannot alter the rewards that we received in the past, which means that on average all these past terms will cancel out with each other. But so if we do not consider them, we avoid adding some noise in this approximation that will send our gradient in directions that are further from the true gradient. So if we can remove some terms from this expression, it is better because we have less chance of introducing noise that sends our gradient into directions that are far from the one that is the true gradient that would be given by this expectation. So the first thing we do is instead of calculating the reward over all the trajectory, we only calculate the reward for each state action of the reward starting from that state action onwards until we reach the end of the trajectory. So this T, big T here, you can see here, capital T, indicates from the time of the current state action that we are considering here until the end of the trajectory. Now, this is one way to reduce the variance of the estimator. Another way is to introduce a baseline. So you can introduce, it has been proven in the research of reinforcement learning that introducing a constant here reduces the variance, and it doesn't have to be a constant, but it can also be something that depends on the state. So it could be also a function of the state for which we are calculating the reward of the trajectory. So for each log probability, we multiply by a term here that indicates the rewards to go, so the reward from this state action until the end of the trajectory, minus a baseline that does not have to be constant, but it can also be a function of the state. And the function that we will choose is called the value function. So this baseline, there are many baselines, but the one we will choose is the value function. The value function tells us of S, according to some policy pi, tells us what is the expected reward if you start from S and then act according to the policy for the rest of the trajectory. This is the value function. Let me show you some examples. So, the value function of this particular cell, of this cell here, we expect it to be high. Why? Because it's very probable that the cat will take the action move down and go directly to the meat. In the case of language model, this is a prompt because it's a series of tokens that we will feed to the language model to generate the probabilities of the next token. And it's very good to be in this state. Why? Because it's very probable that the next token will be generated in such a way that it will actually answer the question of where is Shanghai. So if the model has already generated these two tokens, for example, Shanghai is, it's very probable that the next token will be the word in, and the next token will be the word China, which answers our question, which will result in a good response by the language model, which in turn will give us a good reward according to our reward model. On the other hand, if we are here, for example, with the cat, this is a state that can lead us to move to the bathtub. So we expect the value of this state to be lower than that of this state, because it's less probable that from here we end up on the bathtub. Maybe we get closer to the bathtub, but we do not end up directly on the bathtub. But from here we can end up there. So it will reduce the value of this state. So what is a bad value for a language model, for example? In the case for this prompt here, so we started with a prompt and the language model somehow generated these two words, chocolate muffins, for the question where is Shanghai. Now, if we ask the language model to generate the next tokens for given this prompt, it will probably move far from the actual response of where is Shanghai. It will not tell us that Shanghai is in China. So the value that we can get starting from this state is not so high, because we will probably end up generating a bad response, which will give us a low reward according to our reward model. So this is the meaning of a value function. The value function tells us if I start from this state and then act according to the policy, what is the expected return I can get. Now, how do we estimate this value function? Well, just like we did for the reward model, we can generate a language, we can generate a neural network to which we add a linear layer on top that can estimate this value function. And usually what is done practically is we use the same language model that we are trying to optimize, we add another linear layer on top. So apart from the one that projects into the vocabulary, we add another one that can also estimate the value, so that the parameters of the transformer layer are shared for the language modeling and the estimation of the value. The only two differences are the linear layers. One is used for projecting the tokens into the vocabulary, and one is used to estimate the value of the state, which is the prompt basically. So suppose our language model has generated this response for our prompt. So where is Shanghai? And the language model has said Shanghai is in China. We send it to the policy model, so the language model that we're trying to optimize. This is called the policy. It will generate some hidden states, one corresponding to each token. And then instead of using the linear layer of the vocabulary, so that will project each hidden state into the vocabulary, we use another linear layer that with only one output feature that will be used to estimate the value of each state. So we can estimate the value of this state, of this state, of this state, and also of the entire sequence by using the values generated by this linear layer for each hidden state that we want. Okay, now we have seen that before, to reduce the variance, first of all we transformed the reward of the entire trajectory in rewards to go. So something that starts not from t0 but t equal to the action state that we are considering here. And we also saw that we can introduce a baseline that depends on the state. And this will not change the approximation, so this approximator is still unbiased, which means that it will on average converge to the true gradient but will have lower variance, which means that in the case of, for example, we are calculating the average age of the American population, which means that we are reducing the chance of getting very low values for the age or very high values for the age, but we will get something that is more closer to the true average age of the American population. Now this function here, this rewards to go, is in reinforcement literature is also called the Q function. So the Q function tells us if I start from this state and take this action, what is the future expected reward if I act according to the policy for the rest of the trajectory. So the Q function tells us the expected reward if I start from this state and take this action, so we get some immediate reward, and then act according to the policy for the rest of the trajectory. And so we can simplify the expression that we have seen before as Q of state and action at time steps t, here I forgot the t, minus the value of the state at time step t. The difference between the two is known as advantage function. Now, I know that I am introducing a lot of terms and terminology. Bear with me because it will make sense later. Now, just you don't have to remember all the terms. I will repeat multiple times these concepts. So what we were trying to do, we are trying to reduce the variance of this estimator. And we saw that we can, instead of calculating the reward for all the trajectories, only for the rewards for the starting from the time step in which we are considering the action values. Then we saw that we can introduce this baseline called the value function that will reduce further the variance of this estimator. The difference between these two is called advantage function in the literature of reinforcement learning. And the advantage function, if you look at the expression here, tells us, okay, first of all, let's analyze these two terms. Pen. Now, the Q function tells us what is the expected return if I start from state S at time step t, take action A. So here I forgot the t's, t, action t, and also here t and t. Okay. So the Q function tells us if I start from state t, take action A, and then act according to the policy, what is the expected return. The value function, on the other hand, tells us if I start from state S and I act according to the policy, what is the expected return. Now, in this case, for example, let's use the pen. In this case here, in this state, if I choose the action go down, it is better than going left, because by going down I will move towards the mid, so it is better to use the action go down. The advantage term, that is the difference between these two terms, tells us how better is this particular action compared to the average action that we can take in the state S. which means that the advantage function for the state, for the action go down in this state here, so in this state here, will be higher than the advantage function of another action. So the advantage function tells us how better than the average is this action that we are considering compared to the other actions that we have in this state. And if we want to give an interpretation to this whole expression, it tells our model that for each log probability, so for each action in a particular state, we want to multiply it by its advantage. Because this is the gradient, it will indicate a direction in which we need to optimize our parameters. By using gradient ascent, basically what we are doing is we are forcing our policy to push up, so to increase the likelihood or the log probabilities of the actions that have high advantage, which means that they result in a better than average returns, and push down the log probabilities of those actions in each state that result in lower than average returns. Which means that, for example, let's talk about language modeling. If someone asks, where is Shanghai? So where is Shanghai? What is better, and the question mark, what's a good action to take? What's the good next token to select? Well, we know that the starting with the chocolate is going to be going to produce a reward that is worse than average, because very probably it will lead to a bad answer. However, starting the answer with the word Shanghai will probably result in the correct answer, because the next token will be in Shanghai is in China, so it will actually result in a good answer, which will be rewarded well by our reward model. So our model will be more likely to select the word Shanghai when it will see this prompt. So this is how to interpret this advantage term. Basically, what we are trying to do is we are trying to push up the log probabilities of those actions for a given state that result in better than average reward according to our reward model, and push down the probabilities of those actions given the state that result in low than average reward for according to our reward model. Let's see how to estimate this advantage term now. So first of all, let me write again the expression of the advantage term. So let's use the pen. So as we saw before, the advantage term at time step t, so the starting from state S and taking action t, is equal to the Q function at time step t, action A at time step t, minus the value at time step t. What is the Q function? The Q function tells us if we start from state S and take action A and then act according to the policy, what is the expected return? If we start from state S and take action A and then we act according to the policy for the rest of the trajectory, while the value function tells us what is the expected return if we start from state S and then act according to the policy. Which means that, imagine we have a trajectory. A trajectory is what? It's a list of state and actions. So we have a state 0, action 0, and this will have some reward associated, maybe reward 0. This will lead us to state 1, in which we will take maybe action 1. This will have some reward associated with it, which is reward 1. This will take us to another state, for example, state 2, action in which we will take action 2, and this will have some reward associated with it, which is reward 2. And then state 3, in which we will take action 3, it will have some reward associated, which is reward 3, etc, 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 for the rest of the trajectory. Let's try to understand how can we estimate this advantage term. We saw also before that for the estimating the value function, we can build a neural network, which is a linear head on top of our policy network, which is the language model that we are trying to optimize. So instead of using the linear network, that linear layer that projects the hidden state into the vocabulary, we can use another special linear layer with only one output feature that can estimate the value function of that particular state. Later we will see also how to which loss function we need to use to train this value head. So now let's concentrate on estimating this advantage term. Now imagine we have a trajectory. This advantage term can be estimated like follows. So as we know, the advantage term tells us the Q function. So this is the Q function at given state S and action A at time step t can be calculated as follows. So if we start from state S, we will receive some reward, and then we can calculate, because for each trajectory we can calculate the Q function. So if we start from state S at time step t and take action t in this state and then act according to the policy, we can either sum all of these terms that we have for the trajectory, or we can just say, okay, if I start from state 0 and take action 0, I will have some immediate reward, which is this one, plus I approximate the rest of the rewards with the value function, because I will end up in some state S1, and I just approximate all this rest of the summation as the V of S1. Or we can, let me delete some stuff now because, okay. Now, or we can say, okay, the advantage term, which means that if I start from state S at time step t and take action t, can also be approximated as follows. So I have some immediate reward plus the reward that I get in the next state plus the rest of the trajectory. I approximate it with the value function at time step t plus 2, so S2. And this is exactly what we are doing here. And we are also discounting it with the gamma parameter that we saw here. So we want to discount future rewards. And this minus v is just because of the formula of the advantage term has this minus value function. We can also do it with 3 terms or 4 terms or 5 terms or whatever we want, and then we can cut the rest just with the value function. Now, why do we want to do this? Let me delete some stuff. Okay, if we stop too early, so we calculate, or for example, just the first approximation, because we are approximating most of the trajectory with the value function, it will exhibit high bias, which means that the value of the estimation of this advantage will not be very correct, because we are approximating most of the trajectory with the value function, which is itself an approximation. Or to improve this approximation, we can introduce more rewards from the actual trajectory that we got and only approximate a little bit of the trajectory with the value function. Or we can approximate all of the trajectory with the rewards that we get and use nothing, no approximation with the value head. But if we use more terms, it will result in a higher variance. If we use less terms, it will result in a high bias, because we are approximating more. So in order to solve this bias variance problem, we can use a generalized advantage estimation, which basically takes the weighted sum of all these terms, so of this one, this one, this one, each multiplied by a decay parameter lambda. We can see here. So basically this results in a recursive formula in which we can calculate the advantage at each time step t given the future advantage at time step t plus 1. Let's try to use this formula. For example, imagine we have a trajectory which is a series of states and actions. So we have a state 0 with action 0, which will result in a reward 0. Then we have this will result in another state S1 in which we take action 1, and it will have some reward 1. This will result in a new state S2 in which we take action 2, which will lead us to state 3 in which we take action 3, etc., etc. This one will have reward 3, and this one will reward 2. And this one will have reward 3. Let's try to calculate the advantage. For example, the advantage at time step 3, because it's the last term in our trajectory, is equal to delta at time step t plus gamma multiplied by lambda at time step 4. But we do not have any time step 4, so this term does not exist. So delta 3 is equal to the return that we have at time step t plus gamma multiplied by the value function at time step 4, but we do not have this term because there is no state 4, minus the value of the state S3. This tells us the advantage estimation at time step 3. Then we can use it to calculate the advantage estimation at time step 2, which is A2 is equal to gamma delta 2 plus lambda gamma lambda A3. But what is delta 2? Delta 2 is equal to the reward that we have at time step 2 plus gamma multiplied by the value of the state 3 minus the value of the state 2, etc, etc. So we can recursively calculate the advantage estimation of each term. Why do we need to calculate the advantage estimation? Because the advantage is in the formula of our gradient that we need to calculate the that we need to run a gradient ascent. I know that I have introduced a lot of concepts. I have introduced the value function, I have introduced the Q function and the advantage function. I also know that it may not be very clear to you why we are calculating all this stuff, because we have not seen the code on how it will be used. So please bear with me now. I know that there is a lot of stuff that you need to remember, but when we will see the code, I will go back to all these slides. For now, I just made this all these formulas because later when we go back they will make more sense to you. And also, if you want to in the future review this video, you don't have to kind of watch the code to understand the formulas, because once you understand this video once, you can just review the parts that you're interested and they will be more clarified to you. Okay, now let's see what is the advantage term for language model. So just like the example I made before, I said, okay, we have this expression for our gradient in which we are multiplying each log probability by the advantage function. Also, here I forgot the t, and here I forgot the t. Later I will fix the slides. Now, as we saw before, if we have our question is where is Shanghai, and our language model selects the word Shanghai, very probably this will be a new state that will be fed to the language model for generating the next tokens. The first choice of Shanghai will lead to a good answer, because very probably the next tokens will be selected in such a way that it will result in for example, the phrase Shanghai is in China, which is a good response because it matches what are the chosen answer in our data set of the reward model. So our reward model will give a good reward to this kind of answer. So we can say that this is a good state to be in, because it will lead to future states that will be rewarded well by the reward model. However, if our language model happens to choose the word chocolate as the next token after this question, this new state will lead to new tokens being selected that are not very close to the answer that we are trying to find. This will result in a bad response, so it will result in a low reward from our reward model. So in the case of language models, we are trying to push up the log probabilities of the word Shanghai when it sees the state where is Shanghai, and push down the log probability of the word chocolate when the state is where is Shanghai, because the advantage for choosing Shanghai is higher than the advantage for choosing the word chocolate given this prompt. This is how do we interpret the advantage estimation for language models. Another problem that we have a policy gradient optimization is because of the sampling that we are doing. So as you know, in the policy gradient optimization, the algorithm is like this. So we have a language model, we sample some trajectories from this language model, we calculate the rewards associated with these trajectories, we calculate the advantages associated with these trajectories, we calculate the log probabilities associated with these trajectories. Then we can use all this information to calculate this big expression here, which is the direction of the gradient, so which is the gradient of the expected reward with respect to the parameters of the model, and then we can run gradient ascent to optimize the parameters of the model according to the direction of the gradient. And this is a process that is also used in gradient descent. So usually in gradient descent we have a loss function, we calculate the gradient of the loss function with respect to the parameter of the model, and then we optimize the parameters of the model according to the direction of the gradient. We do this process many times. Why? Because we do little steps with respect to the direction of the gradient according to a learning rate alpha. Now the problem is that we are sampling trajectories from the language model for each step that you are making in this gradient ascent. So for each step of this optimization process, we need to sample many trajectories, we need to calculate many advantages, we need to calculate many rewards, we need to calculate many log probabilities. So this can be very, very inefficient because we will do, when doing gradient ascent, we are taking only small steps. So for each of those small steps, we need to do a lot of calculation, which makes the makes the computation nearly impossible because we cannot run all these forward steps on many different models to calculate the values, the advantages, and the rewards, etc. We need to find a better way. So as you remember, this formula for the gradient that we have found is an approximation of an expectation. And in probability, we have this thing called importance sampling. So when evaluating the expectation with respect to one distribution, we can calculate the expectation with respect to another distribution different from the previous one, as long as we multiply the function inside the expectation by an additional term here. So let's try to understand what does it mean. Imagine we are trying to calculate this expectation, and I want to remind you that in the case of the language model optimization or the gradient policy optimization, we are calculating the gradient of over all the possible trajectory according to policy parameterized by theta of what? Of the reward of each trajectory here. So in this case, the x is, we can consider x to be the trajectory sampled from the policy theta, pi theta, and this could be the reward of each theta. Now, as you know, the expectation can be written as an integral of the probability of each item in the expectation multiplied by the function f of x, which is the inside here in the parentheses of the expectation. We can multiply by this constant here, which is basically the number 1. So we can always multiply by the number 1 in a multiplication without changing the result of this multiplication. So we are multiplying up and down in this fraction by the same quantity, which is the number 1. So we can do it. Then we can rearrange the terms such that we divide the p, basically the p of x by this q of x, where q of x, this term here, is the distribution, is another distribution, is the probability density function of another distribution. And then we can return back this integral to the expectation form. So now we can write the expectation as a sample from the distribution q and calculate with respect to a function that is the f of x multiplied by this additional term. So this means that in order to calculate the initial expectation here, instead of sampling from the distribution for which we want to calculate the expectation, we can sample from another distribution as long as each item is multiplied by this additional factor here. And we can do the same for our expression of the gradient policy optimization, in which we were sampling from some policy here, which is the policy that we are trying to optimize. But we can modify it by using importance sampling to sample from another policy, which could be a different neural network, but we will see that actually it's the same. But okay, suppose that it's a different neural network, because sampling trajectory means that we generate some text given some questions, so it's actually we are sampling from our neural network. And each of the items, so each of this advantage term, instead of being multiplied only by the probability according to the network that we're trying to optimize, we also divide it by this q of x, so this the log probabilities of the distribution from which we are sampling. We will call the distribution from which we are sampling pi offline, and the distribution that we are trying to optimize pi online. Let me give you an example, a graphical example on how it works. So for now, just remember that with importance sampling, we can calculate this expectation by sampling from another network while optimizing another one, a different one. It works like this. This is called off-policy learning in reinforcement learning literature. So imagine we have a language model, and we will call it parameterized by some parameters called theta offline, and we will call it the offline policy. We will sample some trajectories. What does it mean? We give some questions according to our reward model dataset, for example. So we ask it, where is Shanghai? And we ask the language model to generate many answers using a high temperature, for example. Then we calculate the rewards for these trajectories that are generated. We calculate the advantages for all the state action pairs. We calculate the log probabilities for these state action pairs. And then we optimize another model called online policy. So we take all these trajectories that we have sampled from the offline policy, and we save it in some database or in some memory, and we keep it there. Then we take some mini batch of trajectories from this database or from this memory, and then we calculate this expression here, because we can calculate it. So we can calculate the log probabilities according to the online model. So for the trajectories that we have sampled from this memory, we can also calculate again the advantage term according to the online policy, which is another neural network. We can also calculate, and later I will show in the code how it's done. We can also calculate the advantage term according to the online policy. We can also calculate the rewards according to the online policy, etc. And then we run gradient ascent based on this expression, only optimizing this online policy here. And we do it for a few epochs, which means for a few mini batches that we sample from this big memory of trajectories. And after a while, we just set the online policy, the parameters of the offline policy equal to the parameters of the online policy, and we restart the loop. So we start again by sampling some trajectories, which we keep them in the memory. Then for a few epochs, we sample some trajectories from here. We calculate the log probabilities with respect to the online policy. We calculate this expression here, which is needed to optimize with the gradient ascent. And then after a while, we set the offline policy equal to the online policy. Now, they look like two different neural network, but actually it's the same neural network, in which we first sample from the neural network. We keep the memory of the trajectories that we sample, and then we optimize this neural network by taking these trajectories. After a while, we do this process again. I know that this is not easy to visualize, so later we will see this in the code. But the important thing is that now we have found a way to run gradient ascent multiple times without having to sample each time from the policy that we are optimizing, from the network that we are trying to optimize. We can sample once, keep these trajectories in memory, optimize the network for some steps, and then after we have optimized for some steps, we can sample new trajectories. We do not have to do it for every step of gradient ascent. So this makes the computation of this policy gradient algorithm tractable, because otherwise it was too slow to run it. And this is how we do it in the code. So I also created some pseudocode in how to do this offline policy. So imagine we have a model that we want to train. Okay, let's use this one here. Okay, for now just ignore the frozen model, we will not using it. So we have a neural network that we want to train with gradient ascent. So we have a policy that we want to optimize with gradient ascent. We sample some trajectories from this policy, and we keep them in memory. For each trajectory, we calculate the log probabilities, the rewards, the advantages, the KL divergence, etc., etc. Later we will see why we need the KL divergence. For now, just ignore it, this part. Then we sample some mini batch from these trajectories that we have seen. We run the PPO algorithm that we calculated the loss, basically the expression that we saw before. We calculate the gradient using loss.backward, and we run optimizer step, but we do not need to sample again. We just take another sample from the trajectories that we have already saved. We do again another step of gradient ascent, and then etc., etc., until we reach a specified number of steps. And then after we have optimized the model for some number of steps, we can sample new trajectories and then run again this loop of optimization for many steps. So not for every step of gradient ascent we have to sample new trajectories. We sample once, we do many steps of gradient ascent, and then we sample again. We do many steps of gradient ascent, and then we sample again. This makes the training much faster. Okay, I promise this is the last group of formulas that we are going to see. So this is finally the PPO loss. Let's try to understand it. So based on what we have seen before, the first thing that we should see is that this term here is exactly the one that we saw before. So we have the log probabilities according to the policy that we are trying to optimize, divided by the log probability of the policy that we sample from, so the offline policy. Here I don't know why it's so ugly. So we have the log probability of this is called the online policy, so the policy that we are trying to optimize, so let's call it online. This is the log probabilities according to the policy that we sample from, so we sample some trajectories from this policy. This is the offline policy. And then we have this advantage term, which is multiplied by each of the action state pairs. We are calculating the minimum value of this expression and this other expression here, so this clipped log probabilities. Why? Well, first of all, what is the clip function? The clip function says that if this expression we can see here is bigger than 1 plus epsilon, then it will be clipped to 1 plus epsilon. If this expression is smaller than 1 minus epsilon, then it will be clipped to 1 minus epsilon. Why do we want this? Well, it means that, first of all, let's try to interpret this term here, the difference, the ratio of the two log probabilities. So we have some policy that we sample from, and then we have a policy that we are optimizing. This means that if the log probability in the policy that we are optimizing is much higher for a specific action compared to the one that we sampled from, which means that we are trying to increase the likelihood of selecting that action in the future, we don't want this this increase to be too far, so we want to clip it to maximum at this value. On the other hand, if we are trying to decrease the likelihood of an action compared to what it was before, we don't want it to decrease by too much, but at most by this quantity here. This means that in our optimization step, we are moving the action probabilities, so the probabilities of selecting a particular token given a particular prompt, we are changing them continuously, but we don't want them to change too much. We want to make little steps. Why? Because we are if we move them too much, maybe the model will run into maybe the model will kind of not explore enough of the other options. So the model may actually optimize for that particular action too much. So it may always avoid that action, or it will always use that action. In this case, we want to do it little by little. So we want the model to make little steps in increasing a particular action, or a little step in decreasing the log probability of that particular action. Why are we talking about actions? Because we are talking about language models, and so we want to increase or decrease the probability of selecting a particular token given a prompt, but we don't want this probability to change too much. This is why we have the minimum here. So we want to make the most pessimistic update we can. We don't want to be too optimistic. We don't want the model to make the most optimistic step. So if the model is very sure that it can always select this token, we don't want the model to be sure. We want the model to make a little step towards what the model thinks is better choice. The other head that we introduced before was the head for calculating the value function. So as you remember, we also introduced this value function, and we said that this value function, which is a function of the state, indicates what is the expected reward that we can receive by starting from that particular state. And the example that I gave you was, for example, imagine we are our question is, where is Shanghai? So where is Shanghai? If the model has selected, for example, the word Shanghai as the next token, we expect the value of this state, so because this will become a new input for the language model, to be high. Why? Because it will probably result in a good answer that will be rewarded well by our model. But of course, we also need to train our neural network to approximate this value function well. So what we do is we use this other term for the PPO loss is for training the value function estimator. And basically it means we estimate the value function estimator based on a particular state. So this is the output of the model, and we compare it with what is the actual value of this state based on the trajectories that we have sampled, because we have trajectories. Each trajectory is made up of state actions. Each state action has some reward, so we actually can calculate the value of this state according to the trajectory that we have sampled. So we want to optimize the value function estimator according to the trajectories that we have actually sampled from our policy. The last term in the policy, the PPO loss, so we have first of all the policy optimization term, which is this is the one I described here. Then we have the loss because for the value function estimator, and then we have another term here, the entropy loss. This is to introduce some this is to force our model to explore more options. So imagine our model, if we don't have this term here, the model may just optimize the actions in such a way to select the actions that resulted in a very good advantage, to select them more often, and the actions that resulted in a lower than average advantage, to select them less often. So this will kind of make the model very rigid in selecting tokens. The model will always choose the tokens that resulted in good advantage and never select the tokens that resulted in bad advantage. But this will make also the model not explore other options, which means that, for example, imagine we sample some trajectories, and for the question where is Shanghai, the model always selects the word Shanghai because it results in a good answer. But we want the model to be also kind of explore other options. Maybe there is another word, for example, where is Shanghai? Maybe the next word can be the word it, because it will result in it is in China. So we also want the model to give the model the possibility to explore or this more of these options. And this is why we introduce this entropy term, because we want the model for each state actions to also explore other options. So we want to force the model to explore other options. So because we are maximizing this objective here, so we are maximizing this objective function here, we also want to minimize this loss here. We will see later how to do it, and we want to maximize the entropy so that the model can also explore more options. Why we use the entropy? Because the entropy tells us how much kind of disorder there is, uncertainty there is in the prediction. So we want the model to be more uncertain. Why? Because it will help the model to explore more next tokens for a given prompt. The last thing that we need to consider is that if we kind of optimize the policy using the PPO loss that we have described before, the model may learn some tokens or some sequence of tokens that always result in a good reward. And the model may always choose these tokens to always get good rewards. But these tokens may not make sense for us humans. So for example, imagine our model, our dataset forces our dataset for the reward model, forces the model to be polite. The model may just use the word thank you, thank you, thank you continuously, because we know that it is very polite and it results in a good reward. But this is not a good answer for a question, because if I ask you where is Shanghai and you are if the model just keeps telling me thank you, thank you, thank you, then for sure the reward model will give a good reward to this answer because it's a polite answer. But it does not make sense to humans. So we want the model to actually generate output that makes sense, that are very similar to the data it has seen during the training. That's why we want to constrain the model not only to get good rewards, but at the same time to generate answers that are very similar to the one it would generate by just looking at the untrained model, so at the unaligned model. This is why we make another copy of the model that we want to optimize, and we freeze its weights. So this is the frozen model. We generate the rewards for each item, each step in the trajectory, but we penalize by how much the log probabilities at each step change from the frozen model. So for each hidden state, we can generate the reward by using the linear layer that we saw before with only one output feature. But at the same time, for each hidden state, we will also calculate the log probabilities using the other linear layer for generating the logits. So we'll send it also this one to the linear layer to generate the logits. This will calculate the logits and then the log probabilities. So the we do the same for the frozen model, and then we penalize the reward. So this reward here for this time step, we say this is the reward is equal to the reward at the time step 0 minus the KL divergence between the log probabilities of the frozen model, so the log probabilities of the frozen model, and the log probabilities of the policy that we are optimizing. We want to penalize the model for generating answers that are too different from the frozen model. So we want the reward to be maximized, but at the same time we don't want the model to cheat in just getting reward by generating any kind of output, but we want the model to actually get rewards for good answers that are very similar to the one that it would generate if it was not optimized. Okay, I know that you are tired of looking at all this explanation and all this theory, so let's jump into the code now. Okay, so the code that we are going to see is a code that I took from the Hugging Face website, which basically allows us to train a reinforcement learning setup in which we want to train a language model to generate positive reviews. So if we have a language model that is generating text, but we want to force the language model to generate positive reviews of a particular, for example, a restaurant or a movie or something like this. So we want the language model to be still similar to generate something that is comprehensible to humans, but at the same time we force the language model to be positive, to generate positive stuff. So say stuff like, for example, I really like this movie or I really like this restaurant. We will be using the IMDb dataset. So as you can see from the website of Hugging Face, the IMDb dataset, it's a dataset made up of text, of reviews, and for each review it indicates what is if the review is positive or negative. And we will use this IMDb dataset to understand what is the score that we want to give to a review. So if the review will be positive according to this dataset, it will be given a high reward, and if the text generated will be similar to a negative review, then it will be given a low reward. So the first thing that we do is we create the model that we want to optimize, which is this language model here. So it's I think it's GPT-2 already fine-tuned on the IMDb dataset. And then we create a reference model. Why? Because we need a frozen model with frozen weights that we need to keep the weights frozen to compare how different is the response of the model that we are trying to optimize from the frozen model, because we don't want the output to be much different. We just want it to be a little positive, but we don't want the model to just output garbage just to get high reward. We want to actually get actual text that makes sense. This is why we keep also a frozen model. And then we load this PPO trainer. The PPO trainer in Hugging Face is the class that is used to train to run reinforcement learning from human feedback using the PPO algorithm. So let's see first of all what is the reward model. The reward model is basically just a sentiment analysis, or using this model here. It will give us for each text that we feed to this reward model a number that indicates how positive it is according to this IMDb dataset you can see here. So it will tell us if the text that we are receiving is a positive review or a negative review. For example, if we give this text here, it will probably tell us that it's a bad review, so low reward. And if we give this text here for this movie was really good, it will give us a positive reward, and we will use this number here as the reward, so the score corresponding to the positive class. Okay, the first step in PPO is to generate the trajectories. So we have some model, the policy that is the offline policy, and we need to sample some trajectories from it. What do I mean by sampling some trajectories? It means that we give it some text and it will generate some responses, some output text. And what we will be using as a kind of questions or prompt for generating the text, we will be using just some initial sampled text from this IMDb dataset you can see here. So, for example, this dataset is composed of many reviews. Some are positive, some are negative. We just randomly take the initial part of a review and we use it as a prompt to generate the rest of the review, and then we ask the reward model to judge this review that was generated. If it's positive or negative. If it's positive, then it will achieve a high reward. If it's negative, it will achieve low reward. So we take some, we generate some lengths, so random select how many tokens we need to take from each review. We select it randomly. We get these prompts from our dataset and we ask the PPO model to generate some answers for these questions, for these prompts. So generate the rest of the text up to a maximum length that is also sampled randomly. These are our trajectories. For now, these are just the combination of prompt and the generated text. We did not calculate the log probabilities. We did not calculate the advantages. We did not calculate the rewards, etc. Okay, so now for now we only have the query and the response generated by our offline policy. What is the offline policy? Is the model that we are trying to train. So this variable here, model, and now that we have some responses, we can ask our reward model to judge these responses, and we use basically just do a sentiment classification in which we give the response that was given by the policy, and we ask the sentiment pipe, so the sentiment analysis pipes, which will act as our reward model to judge this text. So how positive is this review that was generated? And we will take the score associated with the positive class that will be generated, as you can see here. So as a reward, we take the we assign the reward to the full response. So for each response, we will get one number. And this number is actually the logits, so the score corresponding to the positive class, according to this sentiment analysis pipeline. Now that we have some trajectories, which are some questions, so some prompts, along with the text that was generated, along with the reward for each of these texts that was generated, we can run the PPO training setup. So let's now go inside the code of the library. So the first thing we do is we call this function here step, in which we give out the prompt that we gave to the language model, the responses that were generated, and the rewards associated with each response. And then we run this step function here. Now, the step function here, okay, first it checks if the tensors that you pass it are correct, so the data types and the shapes of the tensors, etc., etc. Then it converts the scores into a tensor, because the scores are at least one score for each response, so it converts it into a tensor. I commented the code that I don't find useful for my explanation, so there are many functions in a Hugging Face, but we will not be using all of them. I will just concentrate on explaining the vanilla PPO like it was described in my slides. Okay, the first thing that we need to do is to calculate all the log probabilities of the actions that we need to calculate the gradient. So we do it here in this function here. So given the answers, the text generated by our model, and the queries that were used, so here they are called queries and responses, but they are actually the prompts and the generated text. The Hugging Face, they calculate the log probabilities for each step. How do they calculate it? Well, they call this function batched forward pass, in which they pass the model from which the answers were generated, so the text was generated, the prompt that were used to generate this text, and they divide each of these questions and responses into mini batches, and then they run it through the model. The model, as we saw in the slides, so let's go back here, I think here, we know that we can calculate the log probabilities corresponding to each position based on the text and the question that was asked. So we can create a concatenation of the question and the text that was generated. We pass it to the model. The model will generate some logits, one for each position of the token. We only take the log probability of the next token because we already know which next token was generated. So we know that for this particular prompt made up of these 4 tokens, the next token is Shanghai. So we only take the log probability corresponding to the word Shanghai. And this is what is done in this line here. So we ask the language model to generate the logits corresponding to all the positions. Then we calculate the log probabilities from these logits. How? Here we calculated the log softmax, so exactly like in my slides. So we calculated the log softmax here, as you can see. So for each logits we calculate the log softmax, which is the log probabilities for each position, but we are only interested in the position corresponding to the next token, and this is done here with the gather function you can see here. So from all the log probabilities, it only selects the one corresponding to the next token because we already know which token was generated. So now we have the log probabilities, and we can save them because we don't have the log. We don't want the log probabilities for all the tokens. We also need to keep track of where the log probabilities start, so the one that we want to consider, and where they end. Why? Because as you can see from my slide, our trajectory here, the question was where is Shanghai? The model generated 4 tokens, whereas Shanghai is in China. So we are only interested in this trajectory, we only have 4 steps. So we are only interested in the log probabilities of 4 tokens. And this is exactly what we do here. So we consider which is the starting point from which we consider the log probabilities and which is the ending token for which we consider the log probabilities, because this the model will generate the log probabilities for all the positions, but we only want some of them, and here is what we do. So we create a mask in which we say to the model only consider, we will be considering only these 4 probabilities or 5 probabilities according to which token were actually generated by the model. So now we have the log probabilities of each action. So let's go back to the step function. Okay, so we calculated the log probabilities according to our offline policy. Why do we do it here inside the step method and not outside? Well, because the Hugging Face is a library that is user-friendly, so they don't want to give to the user the burden of calculating the log probabilities of each action. They do it inside the library, so they only ask the user to generate the responses for each prompt, and then they take care of calculating the rest of the information. Now we also need to calculate the log probability with respect to the reference model, so the frozen model. Why? Because we also need to calculate the KL divergence that will be used to penalize the reward for each position, because we want to penalize the model for generating log probabilities that are much different from the frozen model. Otherwise the model will just do what is known as a reward hacking, which is just generate random tokens that actually give a good reward, but they do not make sense for the user. So we also need to generate using the same method, so this batched forward pass, using the frozen model to generate the log probabilities, which will be used to calculate the KL divergence to penalize the reward. The next step we do is we actually compute these rewards. So how do we compute the rewards? Well, using the log probabilities of the model that we are trying to optimize and the frozen model, because we need to calculate the KL divergence. We have this mask which indicate which log probabilities we need to take into consideration, because we have the log probabilities of all the response, but only some of them are interesting for us because they belong to the trajectory. And let's see how to compute the rewards. So the rewards are computed as follows. So we calculate the KL penalty, which is the difference in log probability. So if you go to here, you can see that the KL divergence is just a difference in log probabilities, as you can see here. And we penalize, as you can see here, the reward is basically just the KL divergence penalization, which is the KL divergence multiplied by some factor, which is the penalty factor. And then we sum the score. So We saw before that the score is what? Is just the score associated to each response by our reward model. Our reward model is just a sentiment classification pipeline that will generate one reward, one single number for each response. So indicating how positive is the response that was generated or how negative it is. Because we only have one generated response, and this response, this reward is associated with the last token. So let me show you in the slides. Here we were computing the reward for each step, but actually the sentiment classification model will compute the reward only for the last token, for the full answer, for the full generated text. So we create, but we need, of course, to calculate the reward of the trajectory, we need the reward for each state actions. So we compute the KL penalty for each positions because we know the log probabilities of the frozen model and of the model that we are trying to optimize. So we have the KL penalty for each position, but we have the reward only for the last one. So this is exactly what we are doing here. We calculate the log probabilities for the KL penalty for each position, but the score is only added to the last token. So here in this position here. And then when we compute the advantage, because we compute the advantage starting from the last to the first, we will kind of take this reward and put it in the previous steps. And we will see this later. So now we have found a way to calculate the rewards associated with each position, in which each position is given some score by the sentiment classification, but this is only given to the last token, while the KL penalty is given to each position. So let's go back. Okay, so we have computed the rewards, and now we can compute the advantages. Let's see how we compute the advantages. To compute the advantages, we need the values. What are the values? Well, the value is the estimation of the value function. As we saw before, the value is computed by using the same model, so the policy network, with an additional head, which is a linear layer that gives us the value estimation for that particular state. So let me show you in the slides. Here we saw before that the policy network, so the model that we are trying to optimize, also has an additional linear layer that gives us a value estimation for each step of the trajectory. And this is actually already, when we calculated the log probabilities, this function also returns the value estimation for each step of the trajectory. Then we can use the values estimated plus the rewards that we calculated plus the mask, because we need to know which value we have and which value we don't have, to compute the advantage using the same formula that we saw before. So we start from the formula of which is this one here. So let's go back to the formula. Okay, here we calculate the delta t to compute the advantage estimation at time step t. So here we are computing first the delta t, which is the reward at time step t plus gamma, as you can see here, multiplied by the value at time step t plus 1, and this is here. So it's 0 if we do not have any future values, otherwise it's the value at time step t plus 1 minus the value at time step t, exactly according to this formula here. You can see here. And then we use this delta value to compute the GAE estimation, which is the delta plus gamma multiplied by lambda multiplied by the GAE at the next time step, which is exactly what we do here. So delta at time step t plus gamma multiplied by lambda multiplied by the advantage estimation at time step t plus 1. And we do it from the last item in the trajectory to the first item in the trajectory. That's why we do this for loop in reverse, and then we reverse it back because we computed the advantage reversed, and then we reverse the computed advantages to have them from 0 to time step t to capital T instead of capital T to 0. Then we compute the Q values that will be used to optimize the value function. So as you can see here, to optimize the value head, so the value estimation, we need to have the estimation of the value function. but according to the trajectory that we have sampled. But what is the estimation of the value function according to the trajectory? It is actually the Q function, because for the value function tells us, okay, let me use some kind of, let me write here, otherwise it's not easy to understand. So the value function here is tells us what is the value of a particular state. So what is the expected return that we can get by starting from a particular state, and we can approximate it also actually with the Q function from the sample trajectories. Why? Because the value function is at time step t is the expected return over all possible actions that we can take starting from the state S and taking action A. So the value function here can be actually calculated from the Q function, but it's an estimated, an expectation over all the possible actions that we can take, which means that the Q function tells us what is the expected return if we start from state S and take action A. The value function tells us what is the expected return that we can get if we only start from state S and we act according to the policy, which is also which basically can also be calculated as the expected return over the Q function, but the expectation over all the possible actions that we can take, which kind of can be thought of as what is the average return that we can get by starting from the state S and taking some actions over all the possible actions that we can take. But we do not have all the possible actions, so we can approximate this expectation with a sample mean according to the one that we have in our trajectory. So we have some actions, state actions in our trajectory, so we can actually approximate this using the QSA that we have in our trajectory. And how do we compute this QSA? As you remember, the formula for the advantage is advantage of SA at particular time step is equal to the Q of SA minus V of S. So we can get QSA is equal to advantage SA plus the value S. And this is exactly what we are doing here. So we are saying to get the Q function, we are calculating the advantages plus values, and this term here will be used to calculate the loss for the value head. We will see later, so remember these returns we are doing here. Okay, so now we have computed the advantages and the values. Now we still are in the first phase, so we have sampled some trajectories from our model that we're trying to optimize. We computed the rewards. Using the rewards, we also computed the log probabilities for each time step. We also computed the advantages for each time step. And we also computed the Q values for each time step, which are used for the value head. Now let's go to the second phase of the PPO algorithm, which is the phase 2, which means that we take some mini batch from these trajectories, we optimize the model based on the estimated gradient, we do it with many steps, and then again we sample new trajectories, we sample some mini batches, we optimize the model according to the loss, we do it many times, and then again we sample new trajectories. So let's go back to our step function. So we are here. Okay, so we computed the advantages. Now we can use the sampled trajectories to optimize the model. So what do? We sample some mini batch. This is the mini batch that we are sampling. So we sample a mini batch, as you can see here, and then what we need to do, first of all, we go, as we saw in the formula of the PPO loss, we need to have the log probabilities according to the model that we sampled from, which is this pi old, and also according to the model that we are trying to optimize using these sampled mini batches, which is exactly what we did here with offline policy. So we sample from some policy, and we need to have the trajectories from this policy and also the log probabilities from this policy, which is the offline policy. And then we use this sample trajectory, so we take a mini batch, and then we run a gradient ascent on an online policy, but we also need to have the log probabilities according to this online policy, the one that we are trying to optimize. And this is exactly what we do here. So we run again this method that we ran before, so the batched forward pass to calculate the log probabilities, the logits, and the value head prediction according to the mini batch that we are considering. And then we train the model according to this mini batch. Let's see how it's done. The first thing that we need to do is to calculate the loss of PPO according to the formula that we saw on the slides. So let's go in the loss. In the loss, we have to calculate 3 losses. The first is the loss for the value head, which is this loss here. So they are actually doing the Hugging Face is actually calculating also the clipped loss, but let's not consider the clipped loss for now. It's just some new, it's just an optimization, but it doesn't have to be in the vanilla PPO. We don't have to do it. So we are taking the values that were predicted by the model and the returns that we calculated as the sum of the advantages plus the values that we saw before. So this is how this is the loss for the value head according to this formula here. So as you can see, so this is basically the estimated Q functions according to our trajectories. And this is the loss of the value head. Then we have the loss of the PPO, which is just the advantage term multiplied by the ratio of the log probabilities. What is the ratio of the log probabilities? It's the here the log probabilities. Okay, let's go to the formula first. Okay, as you can see here, we have the ratio of the 2 probabilities, but we have the log probabilities. So what we can do is we can calculate. Let's use the here. Okay, we have the log probabilities, so the log of A minus the log of B, and then we are doing the exponential of this. This is equivalent to doing the exponential of the log of A divided by B, which is equal to doing A divided by B of the 2 probabilities. So because we do not have the log the probabilities, but we have the log probabilities, we are calculating like this. So we first do the log probabilities of the online model minus the log probabilities of the offline model, and then we apply the exponential, which will result in A divided by B, which is exactly what we want here. So let's check in the code. We are calculating the difference in the log probabilities and applying the exponential, which will result in this ratio here being calculated. Then we need to, this ratio is multiplied by the advantage term, as you can see here. So we need to multiply it by this term advantage. And then we need to also calculate the other part of this expression, which is this clipped advantage, as you can see here. So again, the ratio, but clipped between the value 1 minus epsilon and 1 plus epsilon. So we are doing it here. So the advantage multiplied by the ratio clipped between 1 minus epsilon and 1 plus epsilon. Why do we have this minus sign here? Because the goal in PPO is we want to maximize this term here, but we are doing using PyTorch and the optimizer of PyTorch. PyTorch always run gradient descent, which means that it's the opposite of gradient ascent. So if we want to so it's basically we are, instead of maximizing this, we can minimize the negative loss that we can see here. And this is exactly why we have this minus sign. So because PyTorch always minimizes, we can multiply this by minus, so it's like we are maximizing this term. And the entropy is calculated here, as you can see. Then they have also other terms that we will not use because they do some optimizations, but they are not present in the vanilla loss of the PPO. So the loss of the PPO is calculated as the loss of the policy plus the value head multiplied by its coefficient that you can see here. So loss policy. They calculate also the entropy, but they do not use it. I don't know why, to be honest. So they calculated the entropy here. So they calculated the entropy using the logits, as you can see. And they do it not using the formula that I show in the slides, which is the actual formula of the entropy, but they're using an optimized version called the log sum exp. And I am putting here some information for those who want to have the derivation of how it's done. But basically, Wikipedia says that the convex conjugate of the log sum exp is the negative entropy. And yeah, so we have also this entropy term here, and we return our loss. So let's go back to the optimization step. So we go here. So now we are optimizing over a mini batch, which means that the first thing that we do is we calculate the loss, and then we run a back propagation on this loss, and then we optimize. And we do it for, many mini batches. So let me go back again. So we train on a one mini batch, then we do it again for many mini batches, you can see here, and after a while we return here, and we do again the procedure again. So we again generate the new trajectories, then the Hugging Face library will calculate, and we calculate of course also the rewards. The Hugging Face library will calculate the log probabilities according to these trajectories, the advantage estimation according to these trajectories, the value estimation according to these trajectories. Then we'll iteratively sample from these trajectories some mini batches, and then we run a gradient ascent according to the PPO loss on these mini batches many times, and then again we restart the loop. And this is how we run the PPO algorithm for reinforcement learning from human feedback. Let's go back to the slides, and thank you guys for watching this video. I know it has been very, very demanding. It has been one of my most difficult videos also for me to describe all these parts without getting lost myself. I know that I gave a lot of knowledge because actually PPO and reinforcement learning are quite a big topic, so there are entire university courses on this stuff, so it's not easy to give a complete understanding in just a few hours. This is also one of the reasons I decided not to code it from scratch, because it would make the video like 10 hours of video. But at least I hope that now you have a deep understanding into how each step of the reinforcement learning from human feedback is done. I will share with you the code commented by me with all the parts that are unnecessary removed, or anyway I will comment telling explicitly which parts are not necessary for the PPO algorithm. It took me more than 1 month of research to prepare this video, and I had to record it multiple times because I made some mistakes, and then I realized that I forgot something in the slides, then I had to fix them, etc, etc. So the best way to help me, guys, is to share this video with others if you found it useful. I know that it's very difficult, so I suggest watching it multiple times, because the first time you watch this video you will have some understanding but not very deep. The second time you will realize that you will have a better understanding, and maybe you will need to review some concept from reinforcement learning or from the transformer to better understand it fully. So I recommend watching it multiple times, and please leave in the comments if some part was not clear. I will always try to help you, and yeah, have a nice day.